We're on to part 2 of the hypothesis testing topic, and the first half of this we're just going to think about a couple of areas where hypothesis testing is used and then just do a little bit more theoretical analysis. So remember, the idea of hypothesis testing is to test out a question or an opinion or a view, and we do that by formulating a null hypothesis and then looking for evidence against that null hypothesis in the direction of an alternative hypothesis. Now, an area that is of great interest in a lot of the work that we might do in social sciences, economics and business and so on, is asking the question whether or not there's a difference between this particular group of participants and this particular group over here. So you might, for example, in the case we've got here, be interested in the difference in the average wage for females versus males to see whether there's any kind of discrimination on the basis of gender. But there are many, many examples where we might be looking at differences between groups. Perhaps there are groups of students being taught in different ways and you want to see whether or not the teaching methods have one particular teaching method is better than another. Well, think of one group as the students using method A and the other group, the students learning using method B. And you ask the question whether there's a difference in the average performance across those two groups. So many, many examples where you can frame a question along the lines of differences between groups, and in particular differences in the average performance or the average values, mean values of those two groups. So in this case, we're going to look at the US income data and ask the question whether there's a gender difference in average incomes. And the way we do this is by creating what's called a dummy variable for whether a person's female or not, and you'll get to see how to do this in your workshop. But essentially what you have is a regression model with an intercept, as you're used to having, and the X variable in this case is a column in your spreadsheet which has got the value 0 or 1 for each person. It takes the value 0 if they're not a female, and takes the value 1 if they are a female. So if you've got 5,000 people in your sample, you'll have a bunch of zeros and a bunch of ones, depending on whether the person's female or male. So if a person's female, like I said, the value of the variable here is 1. So what you end up with is the income on average of a female being beta naught plus beta 1 hat indicating estimates. So that's what you get for females, because for females this variable here is 1, so therefore the beta 1 times 1 is included. If you're not a female, or if we're going to treat people in a binary way and say that if you're not female then you are male, then in that case this variable here is 0, and therefore the income of a person on average will be beta naught plus beta 1 times 0, which is just beta naught hat. So in fact, if we consider a regression where we take the incomes as the dependent variable and this column of zeros and ones as the independent variable, then the intercept will provide us with an estimate of the average income for males, and the slope, the beta 1 hat, will give us an estimate of the difference between the average income of females and the average income of males, because you can see here it's the intercept plus the slope that gives you the average income for females. So just subtracting this minus this will give us beta 1 hat, and that's the difference between the average for females and the average for males. So if you want to ask the question, is there any gender discrimination on the basis of wages, you just have to run this regression and have a look at this particular coefficient here and treat it as an estimate of the difference in the average outcomes with the two groups. So that's a pretty convenient thing to be able to do. You can imagine doing that with any groups. Just create a variable that classifies them in 0 or 1, depending on which group they're in, run this regression, have a look at the slope coefficient, and that tells you what the estimated difference is in the means between those two groups. Okay, so that's pretty neat. So what we can then do is ask the question whether or not those differences between the groups is small or big. In other words, so we're back into the world of hypothesis testing. Clearly, in any given sample, you're not going to get these two means being identical to each other. If they're pretty similar and the difference is very small, then you'd say there's no real evidence of discrimination. But if that difference is big, then you would argue that there's some evidence of discrimination. So what we need is a method for judging between kind of small differences, which are just random chance, and big differences, which are evidence to prove that there might be discrimination. And so we think about that using a hypothesis testing problem. If we test the hypothesis that the slope equals 0, that under that null hypothesis of the slope being 0, you'd be saying there's no discrimination, no difference in the average income, because the difference has a mean of 0. The alternative is that there would be a difference. So in order for us to test that hypothesis, we need to come up with a test statistic for the slope. Well, it's actually very similar to the test statistic that you saw in the previous video for the mean. We just take the slope estimate minus the value under the null, which is 0, divided by the standard error of that slope estimate. We see it right here in the regression output. There's the estimated coefficient for beta 1, and here is the t-statistic that goes along with that. And that t-statistic, if you want to see how it's calculated, has been calculated as the estimated value, the beta 1 hat, 5419 or minus 5419, divided by the standard error, 1048. So if you take 5,400 on 1,000, you get about minus 5.169. So that's where that number comes from. Okay, so that's what we've calculated here. And that's what we're going to use to decide whether this difference here is quotes big or small. You can see it's minus 5,000, so that says my estimated income for females is $5,419 lower than it was for males. But so it seems like quite a big difference. But is it just a fluke, or is it a real difference? So hypothesis testing helps us to address that question. Null hypothesis, the slope is 0. In other words, there's no difference between men and women. In this case, we think, if anything, women will be earning less than men, so we assume a negative slope, because a negative slope would indicate that the average income for women is less than that for men. This kind of seems to make sense in this context. We'll choose 5% as we did last time. We'll calculate our t-statistic as minus 5.17, and there's a little discussion there about the meaning of that estimated slope coefficient of minus 5420. But we get a t-statistic here of minus 5.17. We compare that with the t-distribution. We're going to do a one-sided test, so we should be using t-in function. So we've got to just slightly adjust it, because instead of having n minus 1 degrees of freedom, we've got n minus 2 degrees of freedom, because we've got two things we're estimating, the slope for women and the slope for men. The mean for women and the mean for men. So the degrees of freedom is actually 4,690. That makes virtually no difference, but it's just for the sake of being correct, that's what we have to do. And so we get a critical value of 1.65 or minus 1.65. Have a look at your actual value. You got minus 5.17. So quite clearly, you've got clear evidence that this is a long way from 0. This is much, much less than the critical value, much further away from 0 than the critical value. So you would come to the conclusion that there is plenty of evidence against the null. You reject the null hypothesis is the phrase that we use, and you say that there indeed appears to be a very clear difference between the incomes of women and men, and on average women are earning less than men. You can say that less bit because you did a one-sided test. Okay, so that's how we'd apply that to this question of differences in means. Okay, now we're going to digress back to kind of a little bit of the theory of hypothesis testing, because in fact it was a little bit of a pain to have to do things the way we did in that example by looking up the t-in function, and there's a shortcut that we can take which makes use of what's in the Excel output. And that's what's known as the p-value approach. So if you look at the regression output, you'll see that not only does it give us the t-statistic straight away, minus 5.16, but it also gives us something called a p-value associated with that t-statistic of 2.44 times 10 to the minus 7, so a really, really small number. And that number actually can allow us to perform the test quite directly without having to go through the step of finding the critical value, this step here. And the conclusion is not based on whether or not your statistic is less than the critical value, but just whether or not that p-value is small enough. So what is the p-value telling you? Well, it's that the p-value is a probability. That's why it's got a p in front of it. And it's essentially the probability of getting a value for this particular slope estimate, beta 1 hat, a value as far from 0 or further from 0. If the truth was 0, what's the chances of getting a value of in this case, minus 5,420 by fluke? If there was no difference between men and women in terms of average wages, you will get a sample, and you won't get exactly 0 for this coefficient, even though you'd like to. You'll get a number that's perhaps a bit bigger than 0, but less than 0. So what's the chances of getting a number this far from 0, if indeed there is no difference between men and women? Well, there is a tiny, tiny, tiny chance that in your particular sample, you happen to, by fluke, get a few women who didn't earn very much and a few men who earned a lot, and so your sample means were quite different, and so you got a big negative number. There's a tiny chance that might happen by fluke. This tells you what that chance is. And the answer is, it's incredibly unlikely that this value could have occurred by fluke if the truth is that there is no difference between average incomes of men and women. So the logic is, if it's extremely unlikely for such a thing to happen by chance, that's evidence to suggest that indeed this wasn't just a chance outcome, that indeed there is a difference between the average incomes of men and women. So once we get very small values for the p-value, we reject the null hypothesis because such values of the coefficient do not occur by chance, or extremely unlikely to occur by chance. So that's the idea of the p-value. It's the intuition or the logic of it. It's actually really easy to do. All you have to do, and this is just some of the technical side of it, to essentially get the p-value, what you do is you calculate the probability of getting a value of the slope coefficient as far or further from the null. In the case of a two-sided test, that means you've got to look either as far or further in the positive direction or the negative direction. And for a one-sided test like this one, where we're doing less than, we would just be looking at the p-value being this probability in this tail here. So we've just got to do a little bit of adjusting of the p-value that comes from the Excel output. Doesn't really make much difference here, but the p-value that Excel gives you assumes that you're doing a two-sided test. It doesn't know whether your test is one or two-sided, so it assumes two-sided. So it gives you the probability of getting a value as far or further in this direction, and then it kind of doubles it for the possibility that you might be going to plus 5,420. If you're only doing a one-sided test, then you need to take the p-value that Excel gives you and halve it, because you're only interested in the probability of being as far or further in the negative direction in this particular case, given the null hypothesis, the alternative hypothesis that you chose. Okay, so we go to the p-value, it's in the output. We decide whether or not we should divide it by 2, and that all depends on whether you're doing a one-sided or two-sided test. And then you simply, there we are, so you make the decision. So here we're doing a one-sided test, so we take the p-value in the output, we divide it by 2. Really doesn't make much difference. It's so incredibly small that making it half as big is still just making it even more small. But it's so small that it's going to be clear-cut what our decision is. Essentially what we do is we say, if that p-value is less than 5%, we reject the null hypothesis. Well, this is way less than 0.05. It's 0.00000, about 6 zeros with a 2 at the end. So it's tiny, so therefore we reject the null hypothesis. Okay, so that's why we use p-value, because now you can see I can look straight at this Excel output and straight away I can say, right, there's my estimated difference in average salaries of women and men, and that's clearly statistically significant. I reject the null hypothesis that there's no difference, and come to the conclusion that there clearly is a difference. And I can do all of that straight away from the output. I don't have to do any calculations of t-critical values or anything. So that's pretty convenient. The p-value approach and the critical value approach should give you exactly the same conclusion. They're just two ways of answering the same question. One bases it on getting a cutoff point with a set significance level. The other one bases it on getting a p-value. And as long as that's less than the significance level, then your value of your t-stat would also be further from 0 than the cutoff point, the critical value. So they are mirror images of each other. And so they'll always give you the same answer, conclusion. If they don't, you've done something wrong. And don't forget, if you're doing a one-sided test, you have to take the p-value in the Excel output and divide it by 2. Now, back to practicalities. Another interesting problem you might be interested in doing in testing is whether or not there are two proportions are different across two groups. So in the first case, we looked at differences in means across two groups. Now we want to know whether there's some proportion that we're interested in is different across the groups. So in this case, we've got females and males again, just the two groups, and we want to know, is the chance of employment greater if you're a female or a male? So on this time, our dependent variable is a column of ones and zeros as well. It's equal to 1 if you've got a job, and it's equal to 0 if you don't have a job. And our independent variable is the same as before, zeros and ones, depending on if you're female or not. So it's a strange-looking regression. It doesn't fit very well if you imagine a graph with y and x and dots all over the place, because both y and x in this case only take two values, 0 or 1. Clearly there's going to be people who are employed who are female, so they'll have a 1 and a 1. Other people who are employed who are male, so there'll be a 1 and a 0. There'll be unemployed females, 0 and 1, and unemployed males, 0 and 0. So we'll have all the combinations, and we'll have a big set of data with those various mixtures of possible outcomes. If you are female, then there's going to be a 1 here. So this estimated value of beta naught plus beta 1 will be the employment rate, the probability of being employed if you're a female. And if this is 0, then you're a male, then your probability of being employed is just beta naught. So this coefficient beta 1, it's a little bit like the difference between means, is now the difference between the proportion of women who are employed and the proportion of men who are employed. Okay, so it's the same idea intuitively, but instead of being a mean that you're estimating in each case, you're now estimating a probability of being employed, or a proportion or a percentage of outcomes. And so we're asking the question this time by looking at the slope coefficient. Is this slope coefficient 0 is the same as saying, is the employment rate for women the same as the employment rate for men? Okay, so we can run that regression. We can get an estimated difference of 0.02, which says the employment rate in the sample was slightly higher, and then we can look at the p-value to help us decide whether that difference is fluke or whether it's actually statistically significant. Null hypothesis, there's no difference in the employment rates. Alternative, there is a difference in the employment rates. I can get a t-statistic, or I can get a p-value. I'm going to do I can get a critical value or a p-value. I'm going to do a p-value approach this time. It's a two-sided test, so I just go straight to the output and get the p-value in the output, which was 0.00044. That's it there. And then that's less than 5%, so I reject the null hypothesis. So I come to the conclusion that there is a difference between the employment rates of men and women in this population, that result in the sample, which was not 0, is not just fluke, that was a statistically significant result. Okay, so that's the second kind of thing that we can look at. Difference in means in the first half we looked at, and now difference in proportions is another thing. And the only difference between those, you use the same Excel output, but you just define your X and Y variables differently in each case, and there'll be more of those to come over the next videos. Thanks.